All right, let's get a little practice with these continuous functions and try to understand what they mean and what's going on with them. So there's a famous question that comes right after you learn about continuity. We want to choose an a real number, so that this function right here is continuous everywhere. Couple observations. This is a piecewise function. If x is less than 1, then this is how f of x behaves. F of x is a cubic polynomial. We know that for all x's less than 1, this function is cubic, and we know all polynomials are continuous. So for all x's less than 1, f of x is continuous. So all of those are checked off. If x is bigger than 1, then f is a line, okay? So we know that lines are continuous because those are also polynomials, linear polynomials. So f is continuous everywhere past 1. What we need to worry about is f being continuous at 1 itself. So what we want f continuous at 1, x equals 1. That means, therefore, we want the limit as x approaches 1 of f of x to equal f of 1. Now notice, f of 1 in this case is actually given to us. If we're trying to figure out what f of 1 is, we have to figure out what part of our function is actually allowed to take in x equals 1. And it's going to be this top part, because in this top part, x is less than or equal to 1. Okay. And that means if we're going to plug 1 in, we want to plug 1 into this part. 3 times 1 cubed is just going to be equal to 3. So in other words, we want the limit as x approaches 1 of f of x to equal 3. All right. But in order for this to work, we need the limit from both sides. So the limit as x approaches 1 from the left of f of x to equal 3, and the limit as x approaches 1 from the right of f of x to equal 3. Now, this one's obvious. Well, I can say this. We need, or these are the two conditions that we want. We want that to be true, and we want this to be true. One of them was actually already given to be true, and it's this one in particular. But here's the thing. We want the limit as x approaches 1 from the left. If we are approaching 1 from the left, that means that x is less than 1. So this x approaching 1 from the left means x is less than 1, which means that my function actually looks like this top part. So I can replace this function value, this function part, with that 3x cubed, and we want that to equal 3. And that other blue box, if we're approaching 1 from the right, then what does our function look like? This is what our function looks like, because if we're approaching 1 from the right, that means that x is bigger than 1, and this is what we want to plug in for our function f of x right here. So this is the other condition we want. Oh, I think it was ax plus 5. Okay, this one is already true. True. This one, in order for this one to be true, this would imply that this limit's easy to take. We would have a times 1 plus 5 is equal to 3. Oh, but that implies, or a times 1 plus 5 is equal to 3. That implies that a times 1 is equal to negative 2, which tells us what a has to be. A must be equal to negative 2. All right, that's because we had to force the left-handed limit and the right-handed limit to match in order for this condition to be true. First of all, there's a few things you need for continuity. You need this limit to exist in the first place. And if the limit exists, you need the limit to actually equal f evaluated at 1. So you need this to exist, and you need it to equal the function evaluated at 1. And this a equals negative 2 is the thing that accomplishes that. to kind of give you a visual representation for what the heck we just did, here's maybe what our function looks like. Here's x equals 1. For x bigger than 1, x is a line that crosses, well, I'll do x less than 1 first. That's 3x cubed, so that looks something like this. And it has a height of 3 at 1. And then we know that on the other side, we have a line that's going to cross 5 and then has some sort of slope. What we were choosing is the slope. So for instance, we know that our line crosses 5, maybe up here. And then we have this positive slope maybe, but then, so the function actually evaluates at this line past 1. Okay, so that's clearly not going to work. We know it has to cross 5, so maybe let's make a less steep slope. So maybe this is a slope of 0 or something like that. Notice that's clearly not going to work. This does not match, or this part is not continuous with this part. So we're going to have a smaller slope, maybe -1. Still doesn't work. These should all be open circles. And then last but not least, we tried, let's make it a slope of -2. And this one does end up working. So that's what we just did. So this does create a continuous function. It's kind of cool to see. Imagine what you just did. So we had this thing that kind of like could range slopes. That was this part right here, the slope mx plus b. We had a range of slopes, and we wanted to choose the right slope that connected with this part of the function, the 3x minus 1. Okay. So here, I can even add that. So this is my ax plus 5 with a equal to -2. This would be like a equal to -1. This is a equals 0, a equals 1 maybe. Notice the a equals -2 actually works. This one works. And here is my 3x cubed. Okay, so you're forcing something nice to happen, but things can get a little bit more complicated. Sometimes you have to choose 2 numbers. This time I'm going to do it not so officially. I'm going to kind of talk it out, and I think this is going to be okay, especially if you want to, you know, sometimes there's a time restraint on an exam or something. Here's the thing. This is a line, it's continuous. It's mx plus b, or minus b, it's the same thing. That's a line, it's continuous. This is an upside down parabola, it's continuous. So I know all of these x values, my function g is going to be continuous. This time I have to choose a c and a b in R so that this function g is continuous. And I'm trying to convince you that the only x values we have to be worried about are these x values where we transition from this part of the function to this part of the function. That's going to be when x is equal to -1, all right? And then the other time is when we transition from this part of the function to this part of the function. That's when x is going to be equal to 3. But what that means is as we let x values get closer and closer and closer to -1, this function value has to match this function value at -1, okay? So what I'm going to do, this is like hand-wavy mathematics, but we're not proving anything. We simply have to choose a c and a b. We want c and b in the reals such that c times -1 minus b, so that's plugging -1 into this part of the function. We need that to equal, to create a nice transition from this phase of the function to this phase of the function. We need the function values to, as we get x, or as we force x closer to -1, we need these function values to have the same height as these function values on the other side of -1. In other words, what I'm going to do is plug -1 into this x value and force the height here to be the same as the height here. All right. 2b minus c minus -1 squared. Okay, so and then we just figure out what that says. That's -c minus b is equal to 2b minus c minus 1. I don't know, add Oh, look, c's cancel on both sides. Negative c's, that's crazy. Okay, so we have add or subtract 2b, so negative 3b is equal to negative 1. B must be equal to 1/3. All right, that's helpful. But here's the thing. There's another transition we need. We also need the transition from this part of the function to this part of the function to be smooth. In other words, as x hops over 3, we need the height of this function to equal the height of this function, of this part of the function. It's all the same function. And that 2b plus c minus, this time I'm going to plug in 3 squared. And we want that to equal what happens if I plug 3 into this part of the function. So that's going to be 12 plus 5. 4 times 3 plus 5. This simplifies to 2b plus c minus 9 is equal to, what is that, 17? 2b plus c is equal to 26. But b is 1/3. So 2/3 plus c is equal to 26. My favorite way to say 26 is 72 over 3. So 2/3, or I should say this. C is equal to 78 over 3, right? Yeah, 78 over 3 minus 2/3. And that's the same thing as 76/3. That's pretty gross, but at least it's some sort of answer. C is equal to 76 over 3. Huh, that's such a nasty answer. That makes me sus. Okay, let's see. Negative 9, yeah. 2b plus c. (12 plus 5, 17). Okay. I guess it's all good. 76 over 3. All right, let's keep going. Okay, so here's a famous type of question that you guys could get. This is one of my favorites because it's really like an algebra question disguised as a calculus question. We know here that f is continuous. We know that f of 3 is equal to 2. And that this gross limit is equal to negative 6. Okay, so f is continuous, f of 3 is equal to 2, and this nastiness is equal to negative 6. We want to find what the limit as x approaches 3 of g of x is, given it exists. Here's the thing I know. The limit as x approaches 3 of g of x times f of x minus 4 times f of x divided by 3 times f of x minus 5 times g of x. Well, first of all, this is equal to negative 6. I know that's equal to negative 6. But that is also equal to the limit as x approaches 3 of g of x. Oh, that's what we're looking for. Times the limit as x approaches 3 of f of x minus 4 times the limit as x approaches 3 of f of x, all divided by 3 times the limit as x approaches 3 of f of x minus 5 times the limit as x approaches 3 of g of x. All right, so I just used a whole bunch of limit laws. The limit of a quotient is the quotient of limits. The limit of a sum is the sum of limits. The limit of a product is the product of limits. And if you have a number inside of the limit, you can take the number outside of the limit. Okay, I used all sorts of stuff like that. And what I'm going to do is I'm just going to let star equal the limit as x approaches 3 of g of x. So I'm just naming something to make this sentence that I just made a little bit better. And I'm going to also say this. This is really important. Also note that the limit as x approaches 3 of f of x, so this thing and this thing, is equal to f of 3 because f is given to be continuous. All right, so that's at the very beginning. The very beginning, it says, suppose f is continuous. Oh, but I also know that f of 3 is equal to 2. So this is going to simplify a lot. So every time I see this right here, I can replace that with 2 because of this logic. And this logic is really important to say. That's how we were able to do that. This is equal to this because f is continuous. F of 3 is equal to 2 is given to us. And then every time I see a limit as x approaches 3 of g of x, I'm going to replace it with a star. So let's see what that makes. And this is all equal to -6 here. So therefore, -6 is the same thing as star times 2 minus 4 times 2, okay, divided by 3 times 2 minus 5 star. Okay, but that's easy enough. I think 2's cancel. There's a few things I can do. That implies that -6 is equal to 2 star minus 8, all divided by 6 minus 5 star. And therefore, -6 times 6 minus 5 star is equal to 2 star minus 8. -36 plus 30 star is equal to 2 star minus 8. Adding 36 to both sides, subtracting 2 to both sides. Oh, that's kind of nice, I think. Yeah, okay, so we got 28 star is equal to 28. All right, yeah. And therefore, star is equal to 1, and that's giving me my final answer, the limit. So therefore, the limit as x approaches 3 of g of x is also equal to 1. Nice. All right. It was a fun little question, really an algebra question in disguise as a calculus question. I will say loudly, this step right here, I want to make sure you know the limit laws. I think that's LL3 was used, LL4 was used, LL5, and LL6. All of those were used. This was simply a naming convention. I was just saying, hey, let this beast be star, just to make things look better for us. And then this fact was because f is continuous, it's handed to us that f is continuous. And then this fact is also handed to us, f of 3 equals 2. All right, fun question. Let's keep going. Let's see what's next. Okay. So there was a huge theorem that I forgot to bring up in my last theory video. So I'm going to drop it right now, tell you what the theorem is. Before I do that, let me make sure I'm on track. That is the intermediate value theorem. Now, the intermediate value theorem is kind of notorious because it's so easy to explain what the intermediate value theorem says, but it's ridiculous to prove. In the bonus video this week, I'm going to try to give you an intuition for how Bolzano proved it 500 years ago or whatever, 400 years ago. Actually, less than that, like 300 to 400 years ago. It was early 1800s when this first was really rigorously proven by Bolzano. And it still was a little hand-wavy. We still had to wait until Weierstrass, until a more official proof was given. But that theorem is the intermediate value theorem. So I'm going to talk about the intermediate value theorem here. The intermediate value theorem. And actually, you know what? I'm going to spend some time in this video to also talk about another famous theorem when it surrounding the topic of continuity, but we won't apply this other theorem, but I do want to mention it because it's very pivotal in like a week or so. But let's first talk about the intermediate value theorem. Here's what this one says. If f is continuous over a closed interval a to b, so notice endpoints are included. If f is continuous over a closed interval a and b, a to b, and y star is any value between f of a and f of b, then there is some c in the open interval a to b such that f of c is equal to y star. I'm going to draw a picture to illustrate what this means, and you'll be like, oh yeah, that's pretty darn obvious. Remember, continuous functions are functions that you can draw without ever lifting your pen. Okay, so let's say I have an xy graph. Here's A, here's B. I know my function exists over this interval completely. Let's call this f of A. So this would be f of A. And this one up here, maybe f of B. And then I have to let this y star is any value between, so that's strictly between f of A and f of B. I'll call it maybe this one. It's a y value. What this theorem says is there has to be some point in this interval for which f evaluated at that point is on this green line. In other words, even more simply, if I start drawing f, it's continuous. So now that I've started drawing it, I can't lift my pen. The only thing I know about this f is that it has to get to that point up there at some point, that f of b point, but I can't lift my pen. So at some point, I'm going to have no option. I have to get to that point up there. Shoot. I guess I'll just give in. I have to reach up there. What this theorem says is you will always have to cross that green line if you are a continuous function. And if that green line is any line in between these. So that would have also worked for this yellow line, maybe down here. So here's y prime, y star prime. Okay, so what the theorem says is I have to cross that line, but in particular what it says, it's an existence theorem. In other words, there's a point in between A and B that exists, okay? So there's a point in between these that exists. What is that point that we're curious about? It's this point. For that green line, it would be this point C. Okay, so it says C, there is a C in the open interval A and B such that f of C is equal to y star, okay? So for if it was this yellow one, maybe this one, this would be the fancy C, so this would be the C in the open interval A to B, and this would be f evaluated at that C is equal to this y prime, so this would be C prime, I guess. Y star prime, okay. So it says that point has to exist at least once, all right? So this is hopefully very convincing, especially because of the continuity of f, all right? Really crucial theorem. And there's one more I want to talk about that we will also prove. So that's the intermediate value theorem. Notice that C could happen more than once. So for instance, say this was my y star. Then our function kind of crosses that multiple times. So y double prime star, whatever. It crosses here, crosses here, crosses here, crosses here, crosses here. So that's great, but that's more than what the theorem says. The theorem simply says that crossing has to happen at least once, all right? So it could happen a ton of times. It could happen, hundreds and hundreds and billions. It might even be able to happen infinitely many times. Let me think. I don't think so. I don't know. I'll think about that. Yeah, homework. See if it can happen infinitely many times. If it were infinitely many, it would be countably infinite. No, that I was going to say a constant function. Anyways, so the intermediate value theorem, we know it happens at least once. We know the continuous function crosses any line you give us. At least once, could happen 1, 2, 3, 4, 5 times, could happen just once. Okay, but at least once is what the theorem says. All right, really, really crucial. I want to talk about one more. It's called the extreme value theorem. So we have it on our belt. By the way, notice I'm not giving you a proof yet because it's an exhausting proof. It is quite detailed. I'll spend a little time in the bonus video showing at least a proof outline. It'll kind of be like heavy math, proto analysis, or like analysis light or something like that. But it'll be good for me, at least personally. The extreme value theorem. If, this one's also very intuitively true, f is continuous over a closed interval a to b, then f attains its maximum and minimum on a to b. In other words, there are some C and D in the interval a to b such that f of c is always less than or equal to f of x, which is always less than or equal to f of d for each x in this closed interval. So let's draw a picture for what this means. Y-axis, x-axis. Here's an A, here's B, here's maybe f of A, here's f of B. Okay, so this would be B comma f of B. And here's A comma f of A. And what I'm going to do is draw a continuous function. I'm going to make it as obnoxious as possible. All right, so we have a continuous function. It has an x-intercept, stuff like this. What is this theorem saying? This theorem is saying this point exists. This would kind of be the D in the theorem. And it also says that this point exists. This would kind of be the C in the theorem. Notice this. This would be f of D, or D comma f of D. What's special about this value f of D is it is bigger than the rest of the values. That's what this is saying. This f of D right here is bigger than all of these f values. And that biggest f value will always be accomplished, okay, if our function is continuous, okay? That you will always, if you have a continuous function, that this continuous function, it's required that the dots are connected, and it's required that the dots, this dot and this dot, are connected without lifting your pen, okay? So hopefully it's convincing that there's no way you're going to be able to do that without reaching some highest point and then never reaching that highest point again. In the opposite direction, there's no way you're going to be able to do that without reaching some lowest point and never reaching that lowest point again, okay? So that's what this theorem is saying. And this point right here would be C comma f of C. It's another existence theorem. It says that these special points, so these x values, this x value D, is such that f of D is bigger than f of x for all other x's in the interval. That's what that says. And this special C right here is a special point such that f of C is, here, let me say it again. This D right here is a special point such that f of D is bigger than all the other f of x values. So f of d is bigger than all the f of x values for each. So f of d is bigger than f of x for each x in a to b. So if I were to grab all these x values and evaluate f of x, I know that the height of that value is going to be less than or equal to this height. Same thing. I know that f of c is less than or equal to f of x for all these x values. So if I grab f of x right here, so this x value, that's going to be bigger than f of c right here. So that's what the extreme value theorem says. Hopefully that's also intuitively true. Notoriously difficult to prove as well. Okay. Now let's use this. Let's go back to this intermediate value theorem and use it a few times. That's what today's practice video is really mostly dedicated to. All right, but those are two big theorems that we have to know. Notice that these are unique theorems that have to do with continuous function over closed intervals. The beginning of each of these theorems begin the same. F is continuous over the closed interval a to b. F is continuous over the closed interval a to b. All right, so let's see how we can use this. Let's prove that this crazy polynomial has a root. Here's how I'm going to do this. Proof. Notice f is continuous, all right, since it's a polynomial. Nice. Also, notice that f of 0 is equal to, 0 cubed minus 3 times 0 minus 1, which is equal to negative 1, which is less than 0. Okay. By the way, let me remind you what a root is. R is a root of f if and only if f evaluated at R is equal to 0. That's what root means. So a root is an x value that makes the function 0. In this class, well, at least in this type of question, that root is simply a synonym for x-intercept. So what this question is literally asking is, does f have an x-intercept? That's what that is. Does it ever cross the x-axis? Well, here's what we just showed. This function f is below the x-axis at 0. And let's try this one. Oops. Let me use the same color. And f of, let's go with, 3. That's going to equal 3 cubed minus 3 times 3 minus 1, which is equal to 27 minus 10. That is equal to 17, which is bigger than 0. So f spends some time below 0, and f spends some time bigger than 0, but f is continuous. That means that f has to cross the horizontal x-axis. All right, so here's what we said. Let me draw this in purple. So we said at 0, so this is x equals 0, f is equal to negative 1. So this is 0, negative 1. We know f has this height, and at 3, f is equal to 17. So we have 3, 17. But our function is continuous. So by a famous theorem that we just talked about, somehow this function, bing, 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 right here, that r value, that is the r inside of 0 to 3, such that the height of the function value at that r is equal to 0. So the literature I want everybody to have is this. Therefore, by the intermediate value theorem, there is some r in the open interval 0 to 3 such that f of r is equal to 0, and that's literally it. So, I could say this. In other words, f has a root, right? Because that's what this means. If f is equal to 0 at some point, in particular r, then f has a root by definition. Notice that I'm not telling you, this intermediate value theorem doesn't tell you what that root is. It is simply, there is some. It's called an existence theorem. There must exist a root. And that's all that we were asked to prove. We were simply asked, does this polynomial have a root? Is there a root somewhere? We said yes. Not only do we know it has a root, we know that root lives in between 0 and 3. But that is our proof. Finish your proof like a mathematician and move on. So that was our first application of the intermediate value theorem. Typical tactic is to find somewhere where the function is above 0 and find somewhere where the function is below 0. And once you can do that, and also claim that the function is continuous, because we have hopefully proven it at some point, then you can use the intermediate value theorem. So let's see it again. All right, so this is similar. Prove that square root of x plus 1, or root x plus 1 equals 4 has a solution. All right, so this is an intermediate value theorem proof in disguise. Here's how I'm going to begin. Let f of x equal the square root of x plus the square root of x plus 1 minus 4. Okay, so notice what I did is I subtracted 4 from both sides of this equation right here. Why is that a helpful thing to do? Because now the question is, we want to show that f of x, or that f, has a root. Because if it has a root, then I would know that f of r is equal to 0. In other words, the square root of r plus the square root of r plus 1 minus 4 equals 0. Add 4 to both sides, giving us a solution to this equation. All right, so we want to show that f has a root. In order to do that, we better claim that f is continuous. And it is continuous over a restricted domain. What restricted domain is that? We need to make sure we're not taking square roots of negatives. So I think 0 to infinity is going to force that to happen. Notice I can't allow, I can't allow any negatives. Well, this is the more restricted domain part of this function. So f is continuous over 0 to infinity. Also, notice, I don't know, I want to use an x value that has a nice square root. So let's do f of maybe 4. And that's going to equal the square root of 4 plus the square root of 5 plus 1. Or sorry, it's just the square root of 5. I'll do, square root of 4 plus the square root of 5 minus 4. So that is going to equal 2 plus root 5 minus 4. So that's going to equal root 5 minus 2. Okay. Let's see. How are we going to prove or show that this is positive or negative? I think that's definitely going to be positive, but let me argue this. Notice. Let's go with 2 is, 4 is less than 5, which implies 2 is less than the square root of 5, which implies that 0 is less than root 5 minus 2. Okay, nice. So this would be bigger than 0. And then also f of 1, perhaps, is equal to square root of 1 plus, or how about just f of 0? Oh, I can't allow 0. Oh, actually, f is continuous over 0 to open interval. 0 to infinity, but I don't know. Let me just do f of 1. So I don't have to worry about the sort of the edge of its domain. Square root of 2 minus 4. So that is equal to root 2 minus 3. And I'm going to argue that that's less than 0, but here's what how I'm going to do that. Notice that, how about 2 is less than 9, which implies the square root of 2 is less than 3, taking roots on both sides, which implies the square root of 2 is, or minus 3, is less than 0. So that means this guy is less than 0. So I know, therefore, f of 1 is less than 0, which is less than f of 4. And therefore, by the intermediate value theorem, there is some r in 1 to 4. Notice that where the interval comes from, it's the two values that you tested. So that's always going to be the case. There is some r in 1 to 4 such that f of r is equal to 0. Oh, but that implies that the square root of r plus the square root of r plus 1 minus 4 is equal to 0, which implies that the square root of r plus the square root of r plus 1 is equal to 4. And look at what we have. We have an r. We know this r exists. There is some r. That is satisfying the equation. That's what we were tasked to find. We wanted to find an r that satisfies this equation. We wanted to find an x that satisfies this equation. We wanted to show this equation has a solution. That's what we did. Done. Let's try another one. Okay, last one. Same story, guys. Proof. Notice, or I'll start like this. Let f of x equal sine of x minus x plus 1. And notice that f is continuous since sine is continuous and the polynomials are continuous. Therefore, I think it was CL, do I have it in this one? CL, one of the continuity laws, sums of continuous functions, CL1, says f is continuous. Sum of continuous functions. F of x is simply the sum of sine and this polynomial. And the sum of two continuous functions are always continuous. Continuous functions are so well behaved. We want to show that this f has a root. So, notice, I don't know, maybe we can do, what would be the best? F of, it's actually continuous over the reals, so maybe say that, over r. Notice f of 0, that's probably the best, is equal to sine of 0 minus 0 plus 1, which is equal to 1, which is bigger than 0. So now I simply have to find somewhere where this is less than 0. That shouldn't be too bad. Watch this. F of 4 pi is equal to sine of 4 pi minus 4 pi plus 1. Oh, but that is equal to 0 minus 4 pi plus 1. And hopefully that's very obviously less than 0. I don't know. Okay, so you're going to be annoyed with me. 1 is certainly less than pi. After all, pi is the ratio of a circumference of a circle to a diameter. This circumference is certainly bigger than the diameter, so this certainly holds. But that implies that how about this? One is less than 4 pi. So pi is less than 4 pi. And that implies that negative 4 pi plus 1, subtracting 4 pi from both sides is less than 0. Okay. Definitely overkill. So f of 4 pi is less than 0, which is less than f of 0. And therefore, by the intermediate value theorem, there is some r in the interval from 0 to 4 pi such that f of r is equal to 0. Oh, but that implies that sine of r minus r plus 1 is equal to 0, which says that sine of r is equal to r minus 1 for some r. Okay, so we know that r exists by the intermediate value theorem. And now we found a solution to this equation. That's all we need. We showed existence of a solution. That's what was asked of us. So again, the idea with these proofs here are to simply find some place where the function is bigger than 0, find some place where the function is less than 0, and then use and also claim that the function is continuous with some nice mathematics. And then the intermediate value theorem guarantees that this function has to cross 0 somewhere. Okay, there is some r where the function is equal to 0. In other words, the function crosses 0. And the intermediate value theorem, powerful theorem, easy to understand, not too difficult to apply, very difficult to prove. Stay tuned with this week's bonus video.